All right, in this video, I want to talk to you about the second inferential tool that we're working with this semester. The first was confidence intervals, where we were trying to estimate a population parameter, like a mean or a proportion. In this one, we're going to do what's called hypothesis testing. And hypothesis testing is geared specifically for when we want to compare the value of an unknown parameter, think like a mean or a proportion, to some specific point of interest. And I actually have set this up for you a little bit with the way that we interpret confidence intervals. You probably remember that we had a practical interpretation and a theoretical. And really the one that looks like hypothesis testing is when I ask you a question about the interval. Is the mean equal to 22? Is the proportion equal to 0.4? Questions like that. While we saw that we can sometimes have answers or get answers using the confidence interval, are better geared towards the test hypothesis topic. So let me give you a couple for instances. I want to show that the average parking time of all college students exceeds 5 minutes. Now in a confidence interval setting, we would say estimate the average parking time of all college students. But when I have specifically this value 5 that's of interest to me, really what I want to show here is that mu exceeds 5. That's a bad looking greater than sign there, folks, but that's what that's supposed to be, and it's only getting worse. Keep in mind, I am drawing with a mouse. Anyway, mu, parameter, the value 5, and then there's some relationship between them. And that's really what you're going to need to identify. Here's another example. I want to show that fewer than 25% of all college students have at least one tattoo. Well, now the parameter is P. The value of interest is 0.25, and we want to look less than. And so I'll write it this way. P is less than 0.25. Again, confidence interval, we say, estimate the proportion of all college students with at least one tattoo. So we're adding a couple components now. There's a point of interest, a value. When you're working with percentages or proportions, it's got to be between 0 and 1 or 0 and 100%. Means could be really any value at all. I'm going to go one further. Later on, we're going to see how we can use this hypothesis testing technique to do other things too. We've worked with means and proportions so far, but we're going to get to a place where we can compare two means or compare two proportions. And in this example, I want to show that the average SAT scores of current college seniors exceeds the average SAT scores of 2010 college seniors. And so there's a couple ways of writing it, but to make it look like and to think about it the way I've talked about it now, let's do it this way. The mean of the current seniors minus the mean of the 2010. Ooh, this is going to be 2010. I'm trying to subscript it here, and it's not coming out pretty, folks. That's 2010. If I want to show that the mean of the current is larger, I'm going to say is bigger than 0. And for a while, at least, we're going to look at test hypothesis, where the hypothesis we look at has a parameter, mu up here, p, and we're actually going to think of the parameter as a difference between means here. It has some relationship. You see some greater thans and a less than. And then there's a specific value of interest. It was 5 up here. It was 0.25. If I want to see if one's bigger than the other, we use 0 here. And so the added component, there's actually two pieces that are added to the mix now. There's a value, a specific value that we're interested in, and then there's a direction that we're interested in looking. And the directions we're going to find out can be either greater than, less than, or sometimes we have a not equal to. If I wanted to show that the average SAT scores of current college seniors differ from the average SAT scores of 2010 college seniors, I'd use a not equal to here. And we'll develop that as we go through. But that's the general idea of hypothesis testing. It's going to better answer the questions that we tried to answer with our confidence intervals. All right, so here's how I'm going to approach it. I'm going to say that there are 4 steps in a test hypothesis. And each of the videos that I'm making here, I'm going to go through one of the steps. This one, as it turns out, might be our longest video because I did the introduction, and this step takes a while. Formulate the test. But the thing that I always laugh about, and you probably won't think is funny at all, but I'll say anyway, we're going to go through the 4 steps. And my job this semester is to teach all 5 of them to you. And you may say, oh, I heard that wrong. You didn't. There are 4 steps in a test hypothesis, but I am going to show you all 5 of them. And I say that way because one of the steps, and it turns out the way that I approach it, it's called step 3, there's a couple different approaches. And initially, starting off the bat here, I'm going to go with the approach that makes the most sense based upon things we've done and things I know you've seen. So I know you've seen the normal curve and the t-distribution. I know you've worked with sampling distributions. I know that you should be pretty comfortable working with the sampling distribution of x bar. We worked with proportions a little bit. So based upon what we've done, there's a natural first approach to a test hypothesis. And that's what I'm going to talk about in these videos that I'm creating. We're going to come back later and I'm going to say, all right, how about this? And we're going to take a look at another way of approaching the test hypothesis. I'm going to take the step 3 that I talk about in these videos out, and I'm going to replace it with something that is probably going to be a better, more efficient, easier way to work with the test hypothesis. If I showed that to you now, because some of you think, well, why don't we just do that now? It doesn't make sense now. It's hard for me to explain, but it wouldn't make as much sense. So my goal here in these videos is just to give you the big picture, to talk about these different pieces, and then we'll come back later and we'll look at different applications of the test hypothesis, and hopefully you'll see that we're kind of doing the same thing over and over again. Just like confidence intervals, there's one main idea with lots of applications. Same thing here. All right, so let me stop talking about that and let's get into the formulate the test. What the heck does that mean? Well, we're going to be using things called statistical hypotheses. And I guess I should mention, and you've probably heard me say this before, but the test hypothesis topic tends to be challenging for students, more challenging than, say, confidence intervals, primarily because we have a whole set of terminology like statistical hypotheses. We have symbols. You're going to meet some of them in just a bit. And they're weird. They're strange. And so I like to say that it's not an overly difficult idea, but we've layered it with all this terminology and symbols and what I call crap. And it makes it a little challenging. So what I want to do is try to strip that stuff away and see if you can see the idea. And hopefully you'll find that it's not as difficult as it may appear. So we're going to work with these statistical hypotheses. And actually in a test hypothesis, we're going to work with 2 of them. And I'll put them both up at the same time. One is called the null hypothesis. We give it the symbol HO, subscript with an O. Or I'll read that probably as H naught. And this is the hypothesis we hope to show is not true. Now, forget about that other part for a second. I'll come back to it. There's also the alternative hypothesis. So they're kind of competing. The alternative is HA, and that's the hypothesis we hope to show is true. Typically, when someone's telling you what they want to do, we collected some data and we'd like to do this or we'd like to do that. Like, for instance, on the last slide, I said I wanted to show that the average parking time of all college students exceeds 5 minutes. We would write that as the alternative. That's what we want to show is true. We'd write that as the alternative. I want to show that fewer than 25% of all college students have at least one tattoo. I would write P is less than 0.25 as an alternative. And so typically the thing that we're hoping to be able to say is true, and when I say that, we hope to say it's true and attach a measure of reliability to it. That's typically the alternative. The null we then get by default. And what I mean by that is, here's how I'm going to write it. And I know that typically in my notes it makes it easy for me because anything I throw up here in red is stuff you can add in. The alternative, for a while at least, and you're going to outgrow this. We won't outgrow this in a stat 1 setting, but in a stat 2 setting we would outgrow this and we'd see other different ways of writing hypotheses, but the idea will stay the same. We're always going to see that the parameter in the alternative is either going to be greater than, less than, or not equal to some hypothesized value. And that's your task in step 1. You're going to have to try to figure out, what does this story deal with? Is it working with means? Is it working with proportions? Is it working with slopes of regression lines? Are we comparing 2 means? There's going to be lots of applications that we take a look at. You'll get a bunch in stat 1, you'll get more in stat 2. And then you, by default, are going to write the parameter as equal to the hypothesized value in the null. And so the work is done in the alternative, identifying the parameter, identifying the value, and then identifying the direction that you want to test. Because the null, you just take the parameter, the hypothesized value, and throw an equal sign between them. And so that's the first step. We set the hypothesis up. We want to say that the alternative is true. That's what we're hoping to say is true. We begin by assuming that the null is true. Somewhere in your background, you probably did mathematical proofs. Nobody likes them. Whenever I mention mathematical proofs, usually people just want to kind of just go away and just leave me and just be anywhere else but with me. But I bring them up because there was one proof in particular that pertains to this conversation today. And it was a proof by contradiction. And that's kind of the technique that we're setting up here. The proof by contradiction said, well, if you want to say that this is true, let's assume it's not. and let's kind of see where that goes, and eventually reach a contradiction, and there's this big aha moment where you say, well, that must not be true. We're going to assume the null is true. We're going to hopefully reach an aha moment where we say, wait a second, something's wrong here, and we're going to look back up and say, the null hypothesis is wrong. So the first step is identifying the null and the alternative. Please don't call them ho and ha, although later on you'll hear me say ho, and I'll probably say ha too, but typically it's a null and the alternative. You sound more intelligent when you say it that way. That is the end of step one. However, there's a nasty page of notes I got to talk about. And so that's what I want to do next. This next page of notes is really painful. It's not step one. It's not step two. It's kind of stuff. So let's just jump into it. So I'm going to start with this. All right, so what the heck is this? Breathe for a moment. Here's a lot of terminology and crap that I was mentioning, but here's how it plays out. In the bigger picture, think about a population. Typically, we can't gather all that information, can we? It's too costly. But in that population, there is a parameter. Let's talk about a mean. Let's just work with means. But this is true in any application you want to place it on. Let's say that there's a value of mu. We don't know what that is. But we just said, and up at the top of the screen here, I'm going to write a null and an alternative. Let's just say the null hypothesis says mu is equal to 100. I wish I could make a better equal sign. All right, let's do it that way. Mean is equal to 100, and the alternative is going to say mu is not equal to 100. Okay, so somebody wants to show that the mean differs from 100. The null hypothesis, what we're going to assume true is that the mean is equal to 100. Now, here's the problem. We don't know. We don't know what the truth is because we can't sample the entire population. It's too costly. And so what we do is we take a sample. But here's what we know from our sample work, our sampling distribution work. When we get a value of x bar, we can look at that value, but we know that if I take a different sample, what's going to happen to the x bar value? That's right, it's going to vary, right? It's not always going to be the same number. And so we got to try to take a look at this x bar value. We don't really expect it to be perfectly equal to 100, but what if it's 99? That's not 100, obviously, but is 99 far enough from 100 to indicate that the mean differs from 100, or is that maybe just sampling variation? And so we start getting into all those types of questions, and it gets challenging. But ultimately, we're going to take a sample, and based on the sample information, we're going to need to decide, what are we going to do with the null? Because in the true state of nature, the null hypothesis is either true or false. You can't argue that. The mean's either equal to 100 or it's not. And you got to tell me what you're going to do with that at the end. The fourth step, the conclusion, you're either going to reject or accept the null hypothesis. Well, this little table here is just talking about what could happen. Let's say the null hypothesis is really true. Let's say mu is really equal to 100, and you get to the conclusion. We'd want to accept it, wouldn't we? We'd want to say, yeah, accept the null hypothesis. That would be a correct decision. If we rejected the null when the null is really true, that's a mistake. We call that a type 1 error. More terminology for you here, folks. Again, in this video, just try to get broad picture here, big picture, broad strokes. If the null hypothesis is false, so if the mean is really not equal to 100, well, we don't want to accept it. That would be a mistake. We would want to reject the null. And so these two check marks here where I have the word OK written in the table, those would be correct decisions. If the null hypothesis were really true, we would want to accept it. If the null was false, we would want to reject it. And the other two possibilities are called errors. And so in your notes here, I want you to write this. Alpha is the probability of a type 1 error. Beta is the probability of a type 2 error. That's just the probabilities. Alpha is the alpha that we've run into before. We've talked about confidence level, and we can get our alpha from that. Beta is a new probability. We haven't seen that one before. And actually, we don't do a lot with beta, and I'll try to explain in these videos that I'm making. So alpha and beta are the probabilities of making mistakes. Obviously, or at least think obviously, we want these probabilities, because they're probabilities of making mistakes, to be small. So we'd like both alpha and beta to be small. But you know what? They're inversely related. It's a math term. What's that mean, inversely? It means as one gets small, the other gets big. It means if I make alpha really small, beta is going to get bigger. I'm trying to spell the word related here. It's getting ugly. If I make beta small, alpha is going to get big. And so we're kind of at a loss. We're screwed. We can't make alpha and beta both be small. We have to choose one to be small, and then the other one's going to be wherever it is. And here's the worst part. There's no exact relationship between alpha and beta. Alpha and beta don't add to 1 or 0.5. They don't add to anything. We know P and Q in our binomials, they add to 1. But alpha and beta, not so much. And so when we choose one, we forfeit the knowledge of the other. So if we choose alpha, we won't know what beta is. If we choose beta, we won't know what alpha is. And so we're going to have to choose. And the way that we choose kind of goes back to the way we've set this up. And just think about that previous slide. What did we say? There's these two hypotheses. There's the null and there's the alternative. Which one do we want to say is true? We want to say the alternative is true. Which one do we assume is true? Well, we begin by assuming the null is true. So how do I get to the conclusion that the alternative is true? Because that's really what we want to say. Well, we get there by rejecting the null. Does that make sense? We're attempting to say the alternative is true. The reject HO conclusion is the conclusion that says we believe the alternative is true. And when we make the reject HO conclusion, we're either doing the right thing or we're making a type 1 error. And so this is the error. This guy right here, this is the error we're worried about. That's the one we want to have reliability for. And so it turns out we want our alphas to be really small. And so we're going to see in the conclusion step, which is going to be step 4, when I get into the conclusion step and I start talking about the conclusions, we're going to be saying conclusions at alpha equal 0.05. 95% confidence, 0.05, right? At alpha equal 0.01, 99% confidence. At alpha equal 0.10, 90% confidence. We're going to be specifying alpha. But if you ask me, hey, you got alpha 0.05, that's great. What's beta? I'm going to say, I don't know. I'm not sure. And so this little page in notes, there's a lot of information there. Fortunately for us, there's not a lot. I could really drill you on this. I'm not going to. There's usually a question or two on the final exam that come out of this page. But this is the details. This is the stuff that goes on behind the scene. Remember, it's not step 1. Step 1 is just doing what I've got here at the top of the screen. Identifying the null and the alternative that we're going to test. This is just background noise that's there. And that's where I'm going to stop this. So if you can read a story or look at an example and be able to identify the null and the alternative, and again, it ends up being identifying 3 things: the parameter of interest, the value that you're interested in, usually not hidden all that well, and then the direction you want to test. That'll get you to the alternative hypothesis. And then you write the parameter, you write the value, and you put an equal sign between them, and that's the null hypothesis. And I should mention, there's a couple different ways of doing it, and statisticians don't all agree. But if we were doing a greater than test here, if I was testing mu greater than 100, I would still put the equal sign here. If I was doing mu less than 100, I'd still put the equal sign here. Sometimes people would say, well, if you have a greater than here, there's some statisticians would say, why don't you do less than or equal to here? And if you have a less than down here, why don't you do greater than or equal to up here? And there's some statisticians who actually write it that way. I don't. I'm okay if you want to do that. That doesn't bother me all that much. There's some statisticians that drives nuts. It doesn't bother me in the least. Here's why I write the equal sign. If you're doing a less than test or a greater than test, I'm going to put an equal in the null for all of them. 2 reasons. First, it's extremely consistent. It allows me to say, hey, just throw an equal sign in a null hypothesis. And in fact, all the null hypotheses that you ever run into will have an equal component. It may not look like we're doing today on this video, but there's going to be an equal component in the null. And so it's very, very consistent. The second reason I like writing the equal sign is one out of convenience for you. When you look at printouts, you're going to see equal signs on most of computer printouts. All the printouts that we'll use with our software will use equal signs. You'll never see a less than or equal to. You'll never see a greater than or equal to. So I think it's less confusing. I think it's easier and less confusing. And usually when I'm working in a Stat 1 class or a Stat 2 class, easier and less confusing is a good combination. So that's how I'm going to do it. So that's step 1, identifying the null, identifying the alternative hypothesis. Now the next step is to come back and collect some data, but I'll talk about that in the context of step 2. So long.